Yeah, then I welcome everyone to this year's Bolin Center lecture of Research Area 5, which is the research area of historical to millennial climate variability. We have 8 research areas typically at the Bolin Center of Climate Research, and every seminar has 1 annual lecture. And this year we are very happy to have Professor Leo from Ohio State University in the USA to give the presentation about the Holocene temperature conundrum. And I give you some general words about the Bolin Center first, and then I will introduce the speaker. So the Bolin Center was originally founded by Bert Bolin, and he is one of the founding members of the IPCC. And the aim of the Bolin Center of Climate Research is to do interdisciplinary research in terms of climate change, both for the future, but also for the past climates. And that also includes paleoclimate modeling, paleoclimate proxy reconstructions, landscape sciences, glaciology, ecosystem sciences, and typically also meteorology and so forth. So it's a very interdisciplinary center. And today we have the paleoclimate talk by Leo. And then I will hand first, maybe I should say who I am actually. So I'm Frederick Schenk. I'm one of the research area leaders of Paleoclimate Group. The other research area leader is Malin Schilander. And I'm a climate researcher focusing also on paleoclimate modeling and proxy reconstructions. And I work at the geology department here at Stockholm University and part-time at the Swedish Weather Service at the Rossby Center. And I would now hand over to Chong. She knows Professor Lee also personally. I mainly know his papers, but Chong has met him several times. And Chong can then introduce Professor Liu. Please, Chong.
Okay, thank you, Frederick. I'm very happy to invite Liu from Ohio University to give his talk. And I also introduce myself. I'm from Department of Physical Geography in Stockholm University, and I have been in this IA5 research leader for kind of 6 years. So now I briefly have an introduction for Professor Liu. Liu received his PhD in physical oceanography from MIT in 1991. So he has worked extensively on a broad range of topics on global climate changes, from ocean dynamics to climate ecosystem interaction, or from climate changes in the past glacial period to future global warming. So also from this novel dynamic series or new statistic methods, or from climate modeling to data simulation and observational analysis. So it's quite broad. And Liu is one of the most well-known paleoclimate modelers. His contribution to paleoclimate modeling, including all this fundamental understanding on glacier, interglacial cycle, and abrupt changes, and interpretation for abrupt transition happened in past ecosystem, and many other various topics. He has published over 300 papers during past 3 decades and have very high impact in the climate research community. And as Frederick said, personally, Professor Liu is my mentor during my postdoc period in Wisconsin University in early 2000. And he inspired me to finally develop my career in paleoclimate modeling here in Bolin Center. So I'm very lucky to receive his comments and insights on our research frequently. So this is the 3rd time actually that we have Professor Liu in Stockholm and present his latest work that recently published in Nature. So this is just an introduction, and then we give the floor to Liu to start this talk.
Thank you very much, Jim and Frederick. And I'm really glad to give this talk at Bolin Center. So I'll share my screen here.
And comment to the audience. During the presentation, you can type your questions in the F&A section, or later after the presentation, you can also raise your hand, and then you will get the word from us to ask your questions. So now the floor is yours.
All right, thank you very much. So, so I like to talk about something. I actually started about 10 years ago thinking about this. It's global warming or global cooling the last 10,000 years, which is basically the Holocene. Another way to put it, I call it the Holocene temperature conundrum. So the Holocene period, as you've seen here in this figure, let's just for some of you who may not be familiar with this. So this is a global annual mean temperature of the last since pre-industrial. Okay, so we have the global warming here, and this is a reconstruction, the famous hockey stick, and last 1,000 years or so. So you can see that we are ticking up in the last 100 years since pre-industrial, and what we are doing now in this talk is about even longer, 10,000 years. Okay. And so, especially about the issue, there is the Holocene thermal optimum we'll talk about. And just for some of you students may be interested, I mean, this period is kind of interesting because major civilizations started about this time. So it's actually quite important for human society. Also, introduction. If you look at long time span, this Greenland ice core calibrated on temperature, the Holocene is relatively a quiet period compared to the glacier period. Okay, the forcing, however, for the Holocene is actually not small. This shows the major forcing. Just one example from the COMAP, Kutzbach did a long time ago. So it has a summer, very large forcing, about 8 watts per square meter, and winter opposite. Okay, that's a huge forcing. But this is because of perihelion change. And but this is opposite in the, it's a seasonal forcing, annual mean, not strong. And so the strong annual mean forcing, one of them actually is CO2, which is flat here, but has about 20 ppm increase in more precise construction. Another one, of course, is melting of ice sheet and into the Holocene. Okay, so that's annual forcing. So this forcing are critical for our thinking of this issue. And just for some of you who are not familiar with, the perihelion forcing is basically right now we are closest to the sun in December 7th, but about 10,000 years ago it's opposite. We are closer to the sun in January. So at that time in North Hemisphere we have more insolation than today, but in winter you have less. Okay, so that's a major forcing, precession forcing. We're going to be critical here in this talk. Okay, coming back to the issue. Actually, you know, we think about this issue in retrospect. It is, to me, surprising we haven't thought about this issue. Okay, look at this. This is a construction of annual mean, global mean temperature in Marquardt in 2013. And it shows a typical picture we traditionally have been thinking. There is a Holocene thermal maximum about 8,000 years ago, 6,000 years ago, okay? And then actually it's getting colder. And in this reconstruction, you can see that actually this thermal maximum is very warm. It's about ½ degree warmer than then I can't remember which one this benchmark, but it's almost compared to present day. Okay, so so it's very warm actually. But if we think about it, retrospect, it's not obvious. How can we have a global mean annual mean warming 8,000 years ago while our forcing, look at the ice sheet is retreating. Okay, so that will intuitively give you a warming signal. And the CO2 is increasing 20 ppm. That will also give you a warming signal. The insolation, summer, winter, they're opposite. So annual mean is not clear. This will do something. Okay, so annual mean, global mean forcing, it's actually not obvious at all why we will have a maximum 8,000 years ago. Okay, but this is in retrospect. Now, to me, so how is it forced? To me, actually, it was not, I haven't thought about this. It was started actually 10 years ago. I was reviewing a paper for Journal Climate. There's a guy, Dr. Jiang, he was comparing PMIP with China Proxy. He concluded that the title is Considerable Model Data Mismatch in Temperature over China during mid-Holocene, because all the models showed in the Holocene is mid-Holocene, it was colder than today, okay? So, so the model will be here. Model is colder than today here. But the observation Proxy showed is warming. So that's a thermal maximum here, okay? So I thought it was puzzling, and I don't know why. I mean, as a reviewer, I said, well, it's interesting, and you know, it should be published, but I don't know why. But it was in my mind, and I did talk to some paleo proxy people. I said, well, how can you, with pollen, can you get some, you know, annual mean temperature, right? The pollen, the reconstruction, said, yeah, you know, it's tricky, you know, all those things. So there was something in my mind. But then in 2013, Axel Timmerman, I think he was in the working group writing the IPCC 6, I think, 5 or 6, I can't remember 5. And he said, at that time, I was running a trace simulation the last 21,000 years. It's completed. Then he also has one simulation with the Dutch model. And there's UK also use the famous model, also did 21,000 years. And also Peter Clark has 2 of students. One, Shercombe constructed deglaciation part, global temperature. And then this Marquardt construct the Holocene part. It's not published at this time, but I think it was in press, probably something. So the IPCC people knows it. So they put it here. This is reconstruction. These are 3 models. So Axel said, well, we need some figure for the introduction section of something. This is quite nice because they fit very well, and it's quite interesting. And yes, it is very consistent until about Holocene, because I remember that problem. I reviewed that paper before. So I paid attention to here. You see here, this is cooling in the observation, but in the other model, it's warming. So this mismatch is not just for China, and this is for global temperature in the models, okay? And so then I said, well, you know, this, then Axel said, well, yeah, so eventually we said, okay, no. So it was not used at all. So the question is that really it's here. The construction shows some maximum cooling, but the model shows warming, okay? And so to me at this point, then this macro paper come out in like 1 or 2 months. Basically, he used those about 100 or so data around the world, mostly a marine proxy coastal data, and constructed annual mean, global mean, annual mean temperature of this, okay? So as I said, if this curve is regional or some seasonal, then it's not a too big issue. But if it is global mean and annual mean, this is not an obvious problem, okay? Because the forcing we'll come back to details later. So furthermore, he constructed this 30 to 90, so North Hemisphere, middle high latitude, tropics, and Southern Hemisphere, okay? Of course, this signal most clearly is in the North Hemisphere, So this actually probably fits conventional thinking. And it's easy to find the observation. Another proxy shows Holocene thermal maximum consistent. But to me, this is the issue. We have some land data showing the mismatch. We have some marine data shows the mismatch. And so then we look at more detail. We look at the two model again, examine using the true global mean in the model or using the data site mean. Whatever you do, there's no difference. And major, whatever you do, gray line, black line, one I think is using the site. The other one is use true global mean. As long as you use annual mean, global mean, the model is always warming in the Holocene. But the construction, as I said, it was cooling. Okay, so this is issue. Start to think about this issue. About 1 degree difference, and the model is warming by ½ degree. The data is cooling by ½ degree, so it's about 1 degree difference. And it's systematic. The global mean, most clearly in the high latitude, but also in the tropics in the southern hemisphere. Okay, discrepancy. So this is observation. This is a model. So that's why I was puzzled. I started writing this paper. The question to me at that time was, how can global mean annual mean temperature decreases throughout the Holocene against the global warming forcing, the annual mean global warming forcing of rising CO2 and retreating ice sheet? Okay, the insolation is not here because insolation global mean annual mean forcing is 0. Okay, so that's obvious. This is a question. So to me, it is more often it was casted into a data against the model. But to me, the model was just a tool. It's really a data versus understanding. Okay, and as I said, the CO2 rising, retreating ice sheet, leading warming effect. Probably I don't need a model to think about this. Okay, and so that's the issue to me. Okay, and the most puzzling to me was this: you putting the context of global mean, annual mean instead of just regional. We'll come back. And there's always this issue: model versus observation. No, of course, observation is always true. Okay, there's nothing about it. However, especially for paleo proxy, its interpretation can be wrong. Okay, so that's the thing we need to be careful. And same thing for model. A model is never perfect. It's always wrong. However, each model, including the quantitative physical laws, consistent within the system. Okay, so it helps our understanding to address some questions. Okay, so that's the way I like to see the model against data instead of it's really the helping understanding, not just the model itself. So as a modeler, probably in this case, it's better to check self-criticism, right? So what can possibly be wrong in the model? That goes back to the forcing, okay? And this actually is the Marco paper. And this is his construction. Global mean annual mean temperature is cooling. Now he examined all the forcing here. Precession forcing, as I said, it's a seasonal. Annual mean is 0. So January, it's warming. January, which one is warming? This is this normally mean this is warming. January is warming, and summer is cooling. Okay, from high latitude, especially northern hemisphere high latitude, it was cooling. Okay, so this precession forcing annual mean, but annual mean is 0. Okay, and then but there's another forcing obliquity. Obliquity has been decreasing since the Holocene. Now obliquity does have annual mean forcing, but it's regional. What happened is that when you tilt it, when the tilt decrease, you start to have cooling in the high latitude, but warming in the tropics. So the global mean is 0. Okay, so if you pure linear thinking and the homogeneous linear thinking, the radiative forcing is big. It's 8 watts, 10 watts per square meter, which is much bigger than global warming, even present day double CO2 forcing. But Annual mean, global mean, it has no contribution, right? Simple-minded. So at least not obvious what is this forcing, okay? Put it this way. On the other hand, the greenhouse is indeed increasing 20 ppm after after 6,000 years ago, greenhouse gas, especially CO2. That will be about 10% of the doubling CO2. So if the global warming IPCC model shows 3 to 5 degree warming for doubling CO2, it means this CO2 will give you about 0.3, 0.5 warming, okay? But that's the key, is that it's a global mean, annual mean, okay? Regional, locally, this may not be big or seasonal, but for global annual mean, this is a major forcing, okay? Of course, there's also ice sheet. Ice sheet, if you think about the reduced albedo, that probably helps the global mean, annual mean too. Other forcing, not obvious. This is a solar constant. There's no clear trend in this. So it's neither for nor against global warming. There was argument about AMOC, okay? AMOC here. First of all, the construction of AMOC is very uncertain. Secondly, we know AMOC change in the Holocene is very small compared with the degradation period where you have the collapse or whatever. It's very small. Third, the AMOC forcing is not an effective global forcing because it produces a so-called bipolar seesaw, okay? So the AMOC intensifies, it's warming the high latitude, north hemisphere, cooling the southern hemisphere. The annual mean, it's not a very effective forcing. So AMOC is not, to me, it cannot be a too strong annual mean, global mean forcing, okay? Then you go to volcano, okay? Now, the volcano, in my mind, it was, I used the medieval warming as a benchmark because volcano has been recognized important, producing little ice age, okay? But medieval time, it was kind of a quiet volcano. And so if we want to have volcano as a cooling forcing toward the present, it means medieval warming will already have, let's say, 0 volcano. So if you want to be cooling, it means you have to have a negative volcano in the early Holocene. Well, that's impossible. So to me, the volcano cannot be a major effect on the global mean, annual mean temperature to produce a cooling. Okay, so that's why it's not obvious you can have a cooling trend in the data. And now, of course, the model is useful in that it's quantitative for each mechanism. For example, here, if I just hand waving, I say greenhouse wear, ice sheet, I don't know exactly how much is it, right? Qualitatively, I can say it's global warming forcing. And also there's orbital forcing. You can say there's a feedback, land feedback, different feedback. So it may have some net contribution to global warming. That's where I think the model is useful. So this is one model in CCSM3 trace simulation. So you can see that during the Holocene period, just look at the Holocene period, the black line is the warming trend we just talked about, okay? Now, the model also did a couple of simulation, use individual forcing. So the purple one is the one with melting water forcing, including 8.2 events, those kind of things. But you can see that it has very little impact on global mean temperature, okay? Just it's very small. As I said before, first of all, in the Holocene, early Holocene has some melting water, but the AMOC is not an effective global mean forcing. It's because bipolar seesaw. So it doesn't do much. You do see there's two. One is green, that is in this model, ice sheet. You reduce ice sheet, you do see the warming in the early part. And the other one, this is greenhouse gas. This basically follows greenhouse gas, okay? It's a little bit cooling, then actually warming 20 ppm or warming, and finally after pre-industrial warming. And now, so these two, as expected, they are giving you global mean, annual mean warming in this model, each about 0.3 degrees warming in the Holocene. Now, the orbital is a tricky one. In this case, the orbital annual mean, global mean has a little bit of warming, a little bit cooling. So it's not clear what is the orbital effect on global mean annual mean temperature. Okay, and now more or less this is true in other model. That is, oh, when you add them together linearly, is gray line. It's basically reproduce the black line. So that means for global annual mean response in this model, responding to different forcing, it's basically linear superposition. Okay, now that's not obvious results. Okay, because if you go to regional, it may not be linear. Okay, so but at least for global mean, that is the case. And then the other few models, similar thing. The ice sheet give you warming, and the CO2 give you warming. That's consistent in the Holocene. Okay, and the orbital little effect in these two models. Okay, and actually this bar is PMIP. I think it's almost a couple of PMIP, like maybe 50 models. So it's compared with present day. So the on average ensemble mean for PMIP model, it's actually a slight warming. Now you do have model showing cooling for pure orbital effect, 6K, because 6K is mainly basically pure orbital forcing effect. So it's true, some model shows cooling, some model shows warming. The mean probably will say not much change, okay? So that's why here, the warming in the model, our simulation shows that about 0.3 warming in the greenhouse gas and 0.3 warming because ice sheet. This warming actually is okay. The sensitivity, you may say the model is sensitivity too big or too small, but I would say it's probably okay because for the same model, when we simulate deglaciation part, that's mainly driven by CO2. Okay, and they are really comparable. Okay. And so that says the CO2 sensitivity is probably okay with this model. Okay, and so here is our quantitative understanding with model, and with the help of model. Global warming forcing is greenhouse gas about 0.3 degree, ice sheet 0.3 degree. Cooling, we have talk about people well recognize the sea ice rectification of seasonal cycle can lead to cooling. There's vegetation, but vegetation is including the model. Sea ice is also including the model. And so the only thing you can say, maybe they are missing major feedbacks, okay? Because this are already all in the model, in the three models. So the effect is already there. The uncertainty, AMOC, as I said, no clear observational trend, and probably too small for global mean anyway. Volcano, there's no clear trend, and you cannot be a negative volcano in the early Holocene. And when I wrote the paper, well, one review did have a very nice comment. He did suggest the dust aerosol feedback. That is very likely because we know in the mid Holocene, the Africa Green Sahara, so it's weather in summer that will reduce dust. That's possible at that time. You help warming at that time, so it become cooling. Okay. Later we'll show experiment. It does show that at least in one model. Orbital, as I said, no clear systematic warming trend. Okay, and so it's very hard for orbital to produce this trend because you will need to produce 1 degree cooling trend to overwhelm CO2 ice sheet warming to produce a ½ degree cooling in the observation. Okay, so now going a little bit detail, look at the orbital. The orbital, this is the PMIP. I talk about PMIP. You can look at the global mean, zonal mean response in each model. And because the obliquity forcing has about 4 watts per square meter warming in the polar region and about 1 in the tropics, average is 0. So you can see this is systematically produced in all the models. Okay, and you do see the North Hemisphere actually warm more. Now that is because of the sea ice feedback. It's actually known, and just a more recent paper, I think, studied this in more detail, confirmed that this high warming in the middle Holocene, it was because also then the southern hemisphere, even though the obligatory forcing symmetric, it's because precession forcing and sea ice feedback producing this. Okay, but as I said, all of this, when you global mean, the albedo is not obvious. You don't have a big forcing, a big response. Okay, so it does remind us, be careful using regional data to talk about the so-called conundrum issue. For example, if you have high latitude data showing cooling, that's not a problem, okay? Because the model shows cooling too, as I see here, okay? Except a few models, most models show the cooling too, okay? So especially in the North Hemisphere. So if you look at, for example, look at the ice core, you know, the ice core 018 supposed to show temperature in the Holocene. Actually, indeed, most of the ice core showed cooling in the Holocene, but that's fine. That's not evidence against the model, because that's actually consistent with the model. Okay, so we want to be careful when we talk about this issue. Is that in the purest form is global mean, annual mean, not a one regional data to talk about. Okay, now tropics will be an issue. Tropics, the model shows warming, and so if you have a tropics showing a cooling, very strong cooling, that will be very different. Okay, but high latitude is not an issue. Okay, so the dust that we talk about, and it can be effective. In the original model 3 model, we didn't have the dust feedback. So this is just one sensitivity we did with Liu and Gang in Peking University. It just used one of the CSM model. You put a dust there, and you remove dust. You definitely shows warming, mostly in the mid-latitude subtropics. And global mean, you have a little bit change. You can push this up a little bit, okay? But far away from producing this consistent with the observation trend, okay? You can indeed warm up this a little bit, okay? So the dust does help a little bit, okay? But it's insufficient. Maybe in this model, maybe 0.3 degree. But of course, the dust has another issue, is that this is we tested only direct effect. There's an indirect effect, and the dust uncertainty is is so large in all the models. So so that is an issue itself. How do you robustly test the effect of dust, even in the model, because it's so uncertain in the model itself. Now coming back to the proxy, that's a model site. Okay, model site. Most of the effect are already taken into account. The way I put it, known effect are already taken into account. But the dust, maybe additional effect that can help relieve somewhat. The proxy site, you can see that the ocean temperature, and to me, actually, the reason I write this 2014 paper was actually because I saw very inconsistency between two groups of sea surface temperature data. It was this paper, Leduc. He had a paper showing a synthesis of all the sea surface temperature in the Holocene in different regions around the world. What is interesting to see that in this case, the two type of major proxy, one is alkyl, one is magnesium calcium, okay? You see almost in everywhere, these two groups are just opposite. For example, in Eastern Pacific, alkyl shows the warming, and magnesium calcium shows the cooling, and in tropical Atlantic, also it's the opposite. Alkyl shows warming. This will be like the model warming, but magnesium calcium shows the cooling, and in other regions similar, they're opposite. So to me, this suggests that even the data itself has large uncertainty. Okay, at least for the sea surface temperature. Okay, and that made me to start thinking about to write that 14 paper. And this remind me was that well, then I talked to people, right? You work on the proxies here. Is it possible? You have some seasonal bias? Because we know in the Holocene, summer, North Hemisphere, clearly we have a cooling because of the insolation precession signal, okay? Is it possible those are biased towards summer, okay? Maybe some, they say, well, the bugs live the early spring blooms, they survive, then maybe they record summer temperature. And so for me, the test was that in the model context, as a hypothesis, you say, well, what about in the model on those sites, macro sites, if we use model summer temperature instead of annual mean temperature? That's the red line, okay? So in the model, if you use summer temperature, yes, you can indeed produce cooling, although maybe not enough, but you do produce cooling. Very different from the annual mean, which is warming, okay? So, and on each latitude band, global, the cooling, the North Hemisphere, tropics, systematically, but not in South Hemisphere, because the South Hemisphere summer is the opposite. So the summer hypothesis does not work for South Hemisphere, okay? It's something we'll talk at the end, still one major issue. So this is where it will stand, early summary 2014. The question to me is our understanding, how can global mean annual mean temperature decrease throughout the Holocene against the global warming forcing of rising CO2 and retreating ice sheet? So that's the question, okay? It's not about the model or data, it's really the, one hypothesis at that time was that the sea surface temperature, maybe the sea surface temperature in the North Hemisphere was biased toward the summer. That can potentially bias the construction, not as annual mean, but maybe there's some summer, okay? So that was just a hypothesis in the model. And as a modeler, I cannot say anything about the data. And but my collaborator, Yair, and he continued thought about this, I think, from data perspective. Then we work on this. The idea is that, well, because ultimately you still need the data because the model is a model. And if there is seasonal bias in the data, how can we filter it out, right, to get the annual data, seasonal signal, okay? So the idea is that we go back to last interglacial, about 100,000 years ago, when the insolation forcing is big, and the global mean CO2 forcing actually is quite flat. So that's a period probably you have the best signal of seasonal response. Then if we, that region, if we have somehow filtered out the seasonal signal, maybe we can get annual response, okay? So that's the idea. So for those of you who are not familiar with this period, this is a time history here. The Holocene is here. Last glacial maximum, oops, it should be here. Last glacial maximum should be here. And the last interglacial is this period, about 125,000 years ago. The feature here is that you can see in the precession, okay? You see the precession signal in the Holocene is actually not very big, but much bigger in the last interglacial, okay? Just because the eccentricity, so you have this orbital much elliptic, so the Perihelion is much bigger signal here. So that's what we are going to do here. And just also, it's interesting. I mean, this period is the civilization. This period is just the Homo sapien starting. Also, kind of interesting relating to the human evolution. So this is what we did. So they had a core, high resolution core, goes all the way to last interglacial near Papua New Guinea here. And the core itself, you calibrate it with the magnetic calcium temperature, shows this solid line square box in the last interglacial and in the Holocene, okay? Now, as in all previous magnetic calcium data I showed you, Leduc showed, it tend to show a cooling trend, okay? A cooling trend. Certainly you don't have a clear warming trend, okay? That's this solid one. So then what we did is that we know the insolation forcing in this period, and the greenhouse warming forcing is very small, and the mean annual insolation forcing is small. This scale is 10 times smaller than for annual mean than this, so it's basically flat. The annual mean forcing, it's a little bit warming, but it's compared with insolation, is really just flat. Okay, so we want to filter out. We can regress this against the seasonal signal insolation, assuming large linear response overall, and then you are left with a residual. This is the blue square solid line curve. Okay, this is residual. Okay, this is residual. So if it's a linear response, this should be annual mean temperature. Okay, but it's interesting. Once you left this here, it does show a trend, look like the annual mean forcing a slight warming here. Okay, now of course this idea, at least we should test it in the model as far as we can do in the most complex GCM. That's the tool we have, and we had to run it's actually 100 times, but we run the last 300,000 years, so we can use the last interglacial period. That's this dashed line. The dashed line model last interglacial shows this change, very similar to the observation in magnitude. Okay, but there's a offset, but the magnitude is about the same. The trend, especially the trend, about the same. And then we apply this method to this, and as if it's a data. Okay, and then we leave a residual. That's a dash dark blue line. It probably, it's hard for you to tell, but it's here. Now in the model, we do know the true annual mean temperature, SST. That's the cyan line. Okay, so in the model, this says, yeah, at least in the context of this model, this side, it seems to be a quasi-linear response. So if you filter out this seasonal signal, you can, the leftover residual signal, this dark blue one, should be the annual signal. Okay, now you apply the same thing here to the Holocene. You will have, originally you have this response here. After you filter out this, it becomes this blue one, become warming. Okay, same thing. You repeat the exact same thing in the model. The model in the Holocene, you also have this slight cooling here, and in the, I think this fall temperature. And then after you filter the seasonal signal, it becomes this dashed line. So it becomes slight warming. And again, in the model, we have the true annual mean time, and they do go together with the residual. So this basically, the methodology is tested in the model, successful. And then we hope this works for the observation. And so this method, as I said, it's very simple, just a statistical method. You just regress out the insolation seasonal part. You left it with a residual, but it's important to know that the residual a priori, it doesn't have to be annual mean. Okay, we don't know. Okay, it's just a residual. Okay, so if the response is a quasi-linear response to insolation, then they should be annual mean. Okay, so we tested in the model complex GCM. It is so to the extent of the GCM of that GCM, this is tested, and you can apply this to many cores in the tropics region. High latitude we didn't test. It was several reasons. We believe the high latitude, the cores are chosen usually around the frontal region, so it may not be a linear response. So we didn't test that. And also, this actually is not a trivial because you need high resolution data goes all the way to last interglacial. Unlike a macro, that one just for the Holocene, you can find 100 high resolution core. But this, you need the data goes not only Holocene, but also in last interglacial. What we can find is about dozens of this we use here. Okay, so you apply this. This is original SST, and if you apply that, we call it SIT method, seasonal to annual transfer method. But the name was very confusing. Many people tell us. So this is the original SST, and if you do the apply the method, leave the residue, that's the square box, and that's a warming. That's global. I'll talk about. And this is just applied to the model, the line without marker, the model. Okay, this is the original data. You filter out that, become annual data. It's kind of validation of the. But this is for 25 to 40 degree North Hemisphere, and this is tropics, 23 to 23 degree. Okay, and this is South Hemisphere. South Hemisphere. So the tropics has basically same thing. Is that original data tend to be sort of flat, but annual mean tend to be warming in both data and the model. Okay, the South Hemisphere is a little bit tricky, and we'll talk about that later. This is global mean we already talked about. So in this method, you use the data. You don't use model. You apply statistics method. You filter out the seasonal signal, left with annual mean signal. And so this is our results. Original data, this is the one filtered out seasonal signal. We believe this is true annual mean, and it does show warming in the Holocene, consistent with the model. Okay. Of course, in the model, in the trace model, we have separate experiment. We can see that this part of warming is caused by CO2, and there's early part of the warming caused by ice sheet. So the conclusion is that the model data can be consistent if the seasonal bias of the SST is removed. So the original issue is global annual mean against the forcing. The conclusion based on data alone, okay, now is that the SST seasonal bias can indeed be removed by using the larger seasonal signal at the last integration can be removed, okay? And the global mean annual mean temperature has been increasing last 10,000 years due to retreating ice sheet and rising CO2, consistent with our physical understanding and the models. And if this is true, the present day is by far the warmest in global mean annual mean sense in the last 10,000 years, okay? And of course, because it's a glacier, so it was last 100,000 years. We are really the warmest time at that time. Now, so this seasonal bias ocean, and you could also have the Manning data over the land. The land, you could also have bias. Actually, when I was writing paper 14, when I was writing revision, and Michael Mann visited me, visited our department in Wisconsin. Then I was talking to him. He said, "Oh yeah." So he has a paper actually recognize that the borehole temperature can be biased towards the summer. Okay, and he compared that with the Holocene. But the idea is very simple. In winter, you have snow, so the borehole doesn't know air temperature. But in summer, you have no snow, so air temperature, borehole temperature connected. So that's why the borehole temperature is also biased towards summer. Okay, so that was one possibility. And later in our paper, not in our paper, Schumann and Marsick, and they analyzed North American European pollen data and showed that seems like their annual mean actually is more or less consistent with the model. Okay, now that's a part I'm not expertise, so I don't know why the same pollen data, different people get different results. I don't know, okay? But it does show that there's uncertainty, okay, with the data in proxy construction. Even now, more recently, this the new synthesis of Holocene data is still, it shows a different type of pollen, different types. They tend to show this cooling trend, okay, like in the traditional case, okay? Now the marine data now, we sort of say probably they didn't use the seasonal bias, but this still shows a cooling trend. So it's puzzling to me why the pollen data, different people show different results, and how do we calibrate that? Okay, so that's not a question to me, it's a question to data people asking, and why is it? Another thing I think probably it is an issue, even for the hypothesis modeling issue, is that the Southern Hemisphere, because this seasonal bias effect does not work in the Southern Hemisphere. The Southern Hemisphere season is opposite today. If you assume Southern Hemisphere seasonal bias, it will be opposite results, okay? So that's a puzzle that still to me and not clear, okay? So it is an indication that the model is perhaps missing some important feedback, indeed missing some feedback, okay? So to me, Southern Hemisphere is one of the critical test case on this Holocene conundrum issue, okay? But of course, what is missing the model, we don't know, right? It would be nice to know what is missing the model, okay? So, so I think the current understanding is that the retreating ice sheet lead to warming, rising CO2 lead to warming, but if you use seasonal temperature, therefore the enemy temperature is warming, okay? But if you use seasonal temperature, you might be able to get a cooling, okay? So, but the issue against the model is that, well, maybe you say the model bias somehow is not correct in the land feedback, okay? Maybe not strong enough. The marine, since using this, our new method, SAT method, seems like to remove the seasonal bias, and maybe the marine, let's say, model data consistent. But then the land, either the proxy, they have to be consistent, or land or ocean consistency, and or maybe the model has issue, okay? But more clear to me is this Southern Hemisphere, okay? Just the Southern Hemisphere, of course, the problem with Southern Hemisphere is there are so few data in the Southern Hemisphere. So right now the Southern Hemisphere is still not clear. So I think this will be very important to study in the Southern Hemisphere to look at this issue, okay? Because that one at least can test against seasonal summer bias issue will not work. And then what exactly is happening over there, okay? And finally, just we know that we are talking about actually part of the issue related to the controversy about the Holocene. There's a Bill Rodman hypothesis, see that the CO2 is decreasing in the previous 3 cycles after you reach the peak installation here. But in the Holocene, it's increasing, okay? So how can it happen? And his hypothesis that maybe human activity started long before pre-industrial, and human activity, maybe deforestation, maybe some other thing, then coupled with the feedback in the carbon cycle, lead to this increase of CO2, okay? So for the Holocene, you have, for the climate system, has a 20 ppm CO2 rise lead to global warming? This is probably yes. This is what we address the temperature conundrum, okay? You go further, you say, well, the climate ice sheet system, can the 40 ppm CO2 rise stop the last glaciation here, okay? And that's becoming less clear. You will need a climate ice sheet system. And then even broader, in the Earth system, how can the CO2 rise 40 ppm here and different from previous one? Well, that it's an even harder problem because it involves carbon cycle of this issue. So the Holocene actually present not just the temperature, but also go to the entire Earth system. There's still big puzzles that remain to be understand. Okay, thank you. I think that's all. Yeah.
Yeah, thank you very much. That was